Welcome back. Let's now see how we actually train the Q algorithm. As a reminder, don't forget to enroll in my free Udemy tutorial, Vehicle Suspension Control 4, PID Tuning with AI, TD3. You will get the code files and video explanations if you enroll in that tutorial. Also, note that the free coupons that I offer for that, they have limitations in terms of time and the number of enrollments. However, don't worry, I will be renewing them periodically. The standard way to update the Q table and the values in it is using the Bellman equation, which looks like this. Q value at time k plus 1 for some kind of state and action equals the Q value for the same state action pair at time k, so one time step before, plus a constant times the immediate reward at time k for the same state action pair, plus another constant, gamma, times this minus this. So let's go over all of the components in this equation. The first thing that we have to do is to let the agent know what move in a certain state is good and what move is bad in that state. In this particular case, it's very easy. In our grid world, we will give plus 10 points when the agent reaches the goal state, and all the other states will give it minus 1. And it would be this one in the equation. So this one here, that's your immediate reward. Let's say that you are here, your state is 1, 0, first row 0 column, and let's say that you take this action. You move up. Since you move to this state, your immediate reward for this state action pair is this number here, minus 1. So it will equal minus 1. Note that it must be this number here in 0, 0 and not the reward in the cell of origin. The logic is that you start from 1, 0, this cell here, and you move to 0, 0, and it ended up being not the goal cell, but another one. As a result, you got this reward here. If, however, I'm here, so my state is 2, 3, second row, third column, and my action is down, so I move here, I end up getting this immediate reward, which means that R at time k would be plus 10 for this state action pair. If instead I had moved here, if my action had been up, then the immediate reward at time k would be minus 1, which is this number here. However, to determine the value of a certain cell, the immediate reward is not enough. Imagine that you are either in a cell 0, 0 and 1, 3, and then from 0, 0 I move here, and then from 1, 3 I move here. In both cases, the immediate reward would be minus 1. However, logically thinking, this cell here should be more valuable than this cell here if in this cell my action is down and then here my action is right. And that's because this cell 1, 3 is much closer to the goal cell compared to the cell 0, 0. To account for that, we add the so-called future reward to the immediate reward, which will be this term here. This gamma is a discount factor that takes into account the fact that immediate rewards hold more weight compared to the future ones. In other words, I consider them to be more important and more influential than future rewards, and I can regulate that importance with this discount factor. If I make a move and I get some reward now, it has bigger influence on updating the Q value than the future one. That's why the discount factor is between 0 and 1. In my code, it's 0.9. You can imagine that if gamma equals 0, then the future reward has no influence whatsoever on updating the Q value. And if it's 1, then its importance compared to the immediate reward is equal. The other part of this term is this maximum Q at time k, and then you have this new state action pair here. Let's say that you are in this state here, 1, 1. By the way, the subscript k, it means current. When you have this format, then it means that the Q value is evaluated at time k for a certain state action pair. If you had this Q value with k plus 1, then that would mean that this Q value is evaluated in the next time step for some state action pair. You always evaluate Q values for specific state action pairs. However, the subscripts like I and I plus 1, they are about cell position. It tells you whether you're here or here or here. In other words, the subscript I has nothing to do with time. It's about position. And then J and J plus 1, they are for the actions taken. So to summarize, the variable I, it can be this position vector or position tuple, or this one up until this one. So this can be I, or this can be I. And then J can have these 4 values. For example, this can be J, or this can be J. And now, when you are in a state 1, 1, so this is your state vector, and then you take action up, your new state, because of the action that you took, will be this one. You moved upwards, so now your location is 0 row, first column. In that new state, if you didn't have this wall here, let's just imagine that you don't have this wall and the grid world continues upwards, then you would have 4 possible state action pairs from that new state. And these 4 new state action pairs are denoted with I plus 1 and J plus 1 respectively. So just to be clear, this new state here, this new position, I plus 1, you have it because in this state you took this action. But if we imagine that there is no wall here, then an agent in that new state can take 4 new actions. And this is what it's meant here. So you have QK, this is your new state, 0 row, first column, that's your I plus 1, and then you can either have this action, which would be AJ plus 1, or this action, or this one, or this one. Since you have the subscript K here, these are your current Q values at time K in this state here for each state action pair. These are your current Q values in that new state for each action, the ones that you currently have in your Q table at the time when you calculate this Bellman equation. And then you take the maximum of these 4 values, which is why you have this maximum here, then you discount it with gamma, and so the maximum discounted Q value will be the second term in this Bellman equation inside the brackets. However, don't forget that in reality you have a wall here, which means that this state action pair is impossible. You cannot move up any further from this state. Therefore, when you calculate this maximum, this one here is excluded. and you only take the maximum of the remaining 3 entries that you have here in the Q table for this new state in which you ended up because of having taken this action while being in this state first. So in conclusion, you are in this state here and you decide to take this action up, which brings you to this state, which means that your immediate reward will be this one. It will be -1, and then when you are in this new state, you check the current Q values that you have for every state action pair for this new state. You check which state action pairs are actually possible. You know that this one is not possible. You compare all the Q values that are possible, and you take the maximum value, which you multiply by the discount factor, and you get this term here. These two terms, they will give you a so-called target Q value at time k, and then from that you subtract the current Q value, which in our example where we were in this state and we moved here, it would be the number that you currently have in your Q table for this state, first row, first column, and this action, which is up, and this difference will be an error Q value, which is then multiplied by this alpha, which is your learning rate. In my code, alpha is 0.8. With it, you can regulate by how much the Q values are updated. Both the discount factor and the learning rate, they are often determined using trial and error. Finally, this error multiplied by this alpha is then added to the current Q value, which in our example here would be for this state action pair. And then the sum will give you a new updated Q value at time k+1 for the same state action pair. In other words, the entry in the Q table, where this is your row and this is your column, it gets updated. If you loop this Bellman equation enough times, Q values will ultimately converge to some optimal Q values. And once they do, you can apply the optimal Q policy to your agent. Make sure to check the code and explanation in the free Udemy course. You can find the link in the description. In the next video, let's start merging reinforcement learning with control systems. Thank you.